So let's do a review here for our next quiz. I'm telling you, there are going to be a lot of quizzes, and then before you know it, we're getting to the final. Okay, the finals are going to be the last week. I'm going to probably spread them over 2 sessions, Tuesday and Thursday, so make it a little bit less dense. Okay, but quiz 6 is on diagonalization part 1. So not the thing that we did today, but the thing that we did last time. And I'll make it clear what I mean with that. So what I want you to do in each of these questions is to find the diagonal form and tell me what the matrix P is that gets you the diagonal form. And also sometimes I might ask to find the inverse of P or not. So I remind you, right? So we have a matrix A, and the deal is that we're going to find a matrix P here so that we get this equality where this is now the diagonal matrix consisting of the eigenvalues. Now it might be possible, it might be that it's not possible. I can ask this too, right? Is it possible or is it not? Okay, and I'll do 2 examples, but I remind you, go look at the video what exactly it is that how you build P and how you build D and all that. Okay, so the first one I want to do is a 2 by 2. They are very short, quick. They can go very quickly with those. I have it here. Yeah, I'm going to do. Looks like an awful thing, but believe me, it actually is not. So here the question is diagonalizable? Is this diagonalizable? If yes, what is D, the diagonal matrix here? Okay, I'm not asking P here. Okay, so the step 1, as the first thing, of course, this diagonalization is kind of building forward. Oh, I said 5.1. This is 5.2, right? This building onto these eigenvalues. So the first thing we have to do is find the eigenvalues. In other words, we need the characteristic equation. In 2 by 2, this is really not a big deal. Remember, you take the matrix and subtract lambda from the diagonal. And that's the only thing that you do. And then you put this equal to 0. Now 2 by 2, we just work out what it is, product of the diagonal elements. This times that. You have to be very careful for all the negative signs, and then subtract from that the product of the off diagonals. So that is 9 times negative 25. As I said, the numbers look a little bit big, but they are not. I mean, you see. So, okay, minus 14 times, we have to FOIL this out, right? Because we have to solve this equation, so we have to factor it. So we have to, this is not factored, right? Don't bring this to the other side, because that is not a factorization. You have to factor as a product equal to 0, and then you use the 0 product property. I hope you still remember all this stuff from a long time ago. Okay, so we have to FOIL this out. Minus 14 times 16, on my calculator, I found that it is minus 24. And then minus 14 times minus lambda is plus 14 lambda. Minus lambda times 16 is minus 16 lambda. Minus lambda times minus lambda is lambda square. And then minus minus is a plus. 9 times 25, that is 225. Again, use the calculator for this. And this is to be equal to 0. So now you notice the nice thing is here that the big numbers actually kind of disappear a little bit. We have an else lambda square. Taking these 2 like terms, we get minus 2 lambda, and this gives me plus 1 equals 0. And this, if you see it, it is a double product formula, or if you don't see it, you just factor it, and you see you get twice the same factor, namely minus 1, minus 1. So we find lambda equals 1 is the only eigenvalue. Now, this is a case where we don't know whether it's diagonalizable. If there are as many if the number of eigenvalues is the same as the size, then we are guaranteed. Because for each lambda eigenvalue, we get exactly 1 basis vector, and we can put them all together to build P. But if the dimension is bigger, so if there are less eigenvalues, then some of them must have more higher dimension. Okay, so the next thing that we have to do therefore is step 2 is look at the eigenspace. Now there's only 1 eigenvalue, so we only have to do this for lambda is 1. And what is this amount to? That is plugging in lambda equals 1 into this thing here, lambda equals 1. Okay, and then we look at the matrix, not the determinant. So we get minus 15, minus 25, 9, and 61 is 15. Okay. Now it is a little bit ugly in the sense that we get a bit big numbers. So, but we see already we do some row operations to at least reduce the numbers, right? I cannot really get ones here, but let's make the numbers a bit smaller. So I'm going to do row 1 divided by 1/5. Both rows are divisible by 5, so minus 1/5 perhaps because I have no minus sign. And then row 2 I can divide by 3, right? So what do we get then? We get 5, no, not 5, what am I saying? Besides, I like black, let go black. Divided by -5, so I get a 3 here and a 5 there. And over there I get a 3 there and a 5 there. And this now is already clear that we're gonna, even if we don't get the, let's see how far do we have to go, okay? Sometimes you don't really need the actual echelon form with the pivots. Okay, what you see at least is, although you not have a 1, it's no problem to make a 0 in the next row. So let's do this. I would not recommend in bigger calculations, but something small like this, you kind of see what is going on. So here I'm going to do row 2 minus row 1. Because why I'm doing this, well, I'm going to get 3, 5, 0, 0. And I know that this is, it's not a pivot yet, but I know, it was always blue, right? But I know that this is going to be the pivot variable. So x1 is going to be the pivot variable, and therefore x2 is going to be the free variable. Now let's think about it. How many free variables did we need? We needed 2 free variables because we needed a basis of size 2 so that we can build P. We don't have that. So we can work out what the basis is here, but we know already that the basis has only one element, only size 1. And this is too little. Remember, what we needed to have is 2 so that we can put them as columns in P, and then we were done. This means, therefore, that this is a matrix that is not diagonalizable. So, not diagonalizable. Okay? Of course, if you get a problem like this, it's quicker, right? Because now you don't have to do more work. Okay, but I just want to show you that these things can happen, and again, you cannot tell from the size of the matrix or whatnot of the numbers of the matrix whether this is going to happen or not. Okay, so I want to do another one. This time I'm going to do a bigger one. I won't ask you this big one on the test, although you'll see this actually, although it's a 4x4, I prefer 3x3s. It's not too much work. So here's, so next problem, so problem 2 if you want. Where is my matrix? Sorry, to get the right one here. This one, yeah. 3, 0, 0, negative 3, 0, 0, negative 3, 3, 0, 0, 3, negative 3, 0, 0, 0, 0. Kind of a bit boring matrix, right? It's a lot of zeros and a lot of 3s. Notice it's not, oh no, it is, right, sorry, I said that, but I meant to say it's not, it is a triangular matrix. Triangular matrix. It's an upper triangular matrix, to be more precise. So how do you know this? Well, what you need to do is, I'll do this somehow you look at the diagonal here. And anything below the diagonal has to be 0 for an upper, and or everything above it has to be 0 for a lower triangular. Okay. Yeah, you might be a bit confused. Why is it called upper triangular? Because the relevant numbers are in the upper part. The zeros, the stupid numbers, the zeros are in the bottom part. That's why we call it that. And then we know from general theory that the eigenvalues are actually just the diagonal elements. So the eigenvalues are 3, 0, 3, 0. But of course, we're counting each of them twice. Okay, so this means that each of them comes with multiplicity 2, and therefore each of them we should have 2 basis vectors if we want, if have any hope for this matrix to be diagonalizable. If you don't see that this is a thing, just write down so do step 1. I mean, this is step 1, right? But the more traditional way of doing this characteristic equation. So I'll do it here. You just subtract lambda from the diagonal. Oh, sorry, there's a lambda here then. 3, you get a 0, 0, 3 minus lambda minus 3, and 0, 0, 0 minus lambda equals 0. And now you see, for the same reason here, that if it's an upper triangular matrix and the determinant of an upper triangular matrix is just the product of the diagonal elements. So that is 3 minus lambda times minus lambda times 3 minus lambda times minus lambda. Of course, the minuses don't mean anything. And then from this, it's clear that we get exactly these roots. Okay, so that's the eigenvalues. Step 2, we have to find for each of these eigenvalues the eigenspaces. So the eigenspace for x equals, let's start with 3. What do we do? Well, we do as always, we put in lambda equals 3 in here. And what do we get? Okay, so let's see, 3 minus 3 is 0, and 0, 0, negative 3. Then 0, what do we put in 3? So we get a negative 3 there, and we have a negative 3 and a 3. And then we get 0, 0, 3 minus lambda is 0, negative 3. And then we get 0, 0, 0, negative 3. Okay. Luckily, a lot of trees, so we kind of factor out all these trees. Okay, so row 1 minus 1/3 of row 1 and row 2 minus 1/3 row 2. I'm doing the minuses so that the first element is always a plus 1. It's easier. Same there, and same for the last one. So we get actually 0, 0, 0, 1, 0, 1, 1, negative 1, 0, 0, 0, 1, 0, 0, 0, 1. Now, the first pivot is this guy, so we have to swap the two rows. Okay, row 1 and row 2, let's swap them. We could have done it right away, but okay, I'll take my time. So we get 0, 1, 1, negative 1, and then we get 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. Of course, you see that the last two rows are going to disappear, but the next, so this is one pivot, this is going to be another pivot, and then we do row 3 minus row 2, and the same for row 4. Okay, so we get 0, 1, 1, negative 1, 0, 0, 0, 1, and the rest are 0 rows. I'm going to write it one more time, but then from then I'm no longer. Okay, so we know what the pivots are, but let's go all the way to reduced echelon form. Some of you don't want to do this, and I can imagine sometimes you make a mistake and then your matrix gets so ugly that you don't want to do it. Normally, the matrix that I give you are neat enough that you don't, it's not such a big deal. But I really would advise going, if you need to, right? And in this case, we need to, because we need a basis for the null space of this matrix, right? The eigenspace for lambda is 3, where I said x is 3. For lambda equals 3, we need to take the, for this matrix, that is the matrix where we subtract lambda from the diagonal, we need to find the null space. And that means we have to solve the system of equations. That means we have to go to the reduced echelon form. Okay. So let's do this with this one more row operation here, which is to get a 0 there, right? And that is row 1 plus row 2. Because these are very trivial operations here, that are calculations, right? Okay, and I'm not going to write the other two. Okay, let's analyze it. We are in the reduced echelon form. We have the two pivots. So x2 and x4 are the pivot variables. And then the other two, x1 and x3 are the free variables. And this is exactly what we wanted, because we saw that lambda equals 3 comes twice, so we needed two basis vectors, and we have that. So hopefully the same happens with 0, so that we can diagonalize. Well, I don't know whether you want to hope this or not, because then otherwise you're finished, right? Okay. So here. Yeah, I didn't say what I wanted here. Here I want to also, what is P, what is D, if they exist. Okay? So the whole spiel, and also what is P inverse. Which can be another nuisance, but you'll see it's not that bad here. Okay, so we have x1, x2, x3, x4. Be very careful with this. I have sometimes make mistakes too. The green ones, the free variables, are equal to themselves. So x2, we see that from this equation that x2 is minus x3, and from this equation see that x4 is just 0. So we get x3, and then we have 1, negative 1, 1, 0. Sorry, what am I saying here? I'm sorry. Okay, what I'm saying. Whatever I said was wrong, but then at the last step I made a mistake. Sorry, I was thinking of something else already. Okay, so here, let's take our time. I was rushing it. So we have two free variables, x1 and x3. We have to take out one of them, and that is it only appears here 1, 0, 0, 0, and also the other one that is 0, minus 1, 1, 0. Okay, these are the two for lambda equals 3. So now let's do lambda equals 0. Now, of course, lambda equals 0 means that you subtract 0 from diagonal, means you're dealing with the original matrix. So I'm going to write down the original matrix again. You can just see, yeah, this is what it was. Trust me. 0, 0, 3, negative 3, 0, 0, 0, 0. Okay. Again, a lot of 3's can go out here. So row 1 divided by 3, row 2 divided by 3, or negative 3 perhaps. And then row 3 divided by also by 3. And we're already lucky with the last row. Okay. So we get 1, 0, 0, negative 1, 0, 0, negative 1. No, 1 because I divided by negative 3, right? So 1, negative 1, 0, 0, 1, negative 1. We see what we need to do. Sorry. Right. This pivot, everything is taken care of, but this one we have to do something. So row 3 minus row 2. This gives us, let's see, 1, 0, 0, negative 1, 0, 0, 1, negative 1, 0, 0, 0, 0. And remember, I already didn't write the last row 0 anymore. Okay, so an analysis tells us again we have two pivot variables, x1 and x3, and two free variables. And that's the one that the number we needed to have. We needed also 2 here because lambda equals 0 was twice a root, and therefore we need 2 basis vectors, which we have. So x1, x2, x3, x4. So x2 is equal to itself, and x4 is equal to itself. What is x1 to? Yeah, sorry, I got a little bit. So x1 is equal to, let's see, from this equation we see that x1 is equal to x4. And x3 is also equal to x4. Well, we had x4 here, right? Yeah. Okay, so what do we get? x2, we get 0, 1, 0, 0, plus x4, 1, 0, 1, 1. Let's see. Yes, okay. All right, so we have the right amount, we can build P. Now, again, the choice of P is not fixed. You could choose different bases, and it gives you different P's. Also, the order in which you put them is not fixed. But when we put the order, you have to be very careful that at the same time you make the same choices for your diagonals. So let's work out in the order that we found them. For lambda is 3, we found these two. So I'm going to put these as the first 2 columns. In which order, that doesn't matter. So there's 1, 0, 0. And the other one was 0, minus 1, 1, 0. 0, minus 1, 1, 0. And so this was corresponding to 3. The other 2 was 0, so that's where they will go. And their eigenvalues are these 2 ones. And again, in which order I write them doesn't matter. And you could have probably written it in a different order. That's fine too. There's an obvious order because of the numbering of the variables, but that's not really what you need to follow. Okay, so here is our P. The rest, of course, is diagonal matrix, everything is 0 here. So now we have to find P inverse. So we have P and D. What is P inverse? Now, since there are so many zeros and ones, it's not going to be hard. Remember, I just wanted to show you how you do this on a 4x4. we augment it with the identity matrix, and while we put the left-hand side into the identity matrix, the right-hand side becomes magically our P inverse. Okay, let's see, where am I? Oh, this is good. This one I need a +1 here. I could switch the two rows. Let's switch the two rows. I'm lazy. Okay, so I'm gonna switch the two rows. So that will give me, now once you have decided P inverse is completely determined, there you cannot have any freedom anymore, right? So although I have choices in what I do, eventually I will get the same matrix. Everybody should have gained the same matrix. If you started with this P, if you start with a different P, of course you get something else. Okay, so that gives me 1 0 0 1 1 0 0 0 0. What was I doing? Switching them. 1 0 1 0 switch 0 0 1 0, and then 0 minus 1 1 0 0 1 0 0. Remember, the whole tail has to do the same thing, right? 1 and 0 0 0 1. Okay, we have our one pivot is this pivot, so we need to make that number underneath there 0. So row 3 plus row 2. Okay. We get 1 0 0 1 1 0 0 0 0 1 0 1 0 0 1 0, right? And then we add 0 0 here, a 1 we add, this is a 0 here. I keep reading this wrong, so let me make this correct here. So we're adding there a 0 1 1 0. Then I have 0 0 0 1 0 0 0 1. Okay, very good. All my pivots, I'm in echelon form already. I have to make a reduced echelon form, and there's only something that has to be done in the last column here, so in other words with the bottom pivot. So I'm going to do row 1 minus row 4, and the same with all the two other rows. It's not an arrow, that is minus row 4 and row 3 minus row 4. Sorry, a bit sloppy here, minus 7. Okay, you know what I mean. Okay, so let's do this. So we're subtracting, right? So we get 1 0 0 0 1 0 0. In other words, we multiply this with -1 and add up there, so that's a -1 here. We do the same here. This becomes a 0, and then 0 0 1. This is going to give me a -1 0 0 1 0 now, and then here we get 0 1 1, and then we get a -1, and this just stays as it was. And there is our inverse matrix. Okay. All right, and that's so this is P inverse. And now, as a final test, we could work out what is P inverse AP. Okay, let's work it out just to double check. This is I might not ask you to do this, but you'll see. But if you remember what we did today, actually, this is the kind of thing we need to do anyway, or at least after we take a power. But okay, let's do it now. Then A, do I still A? No, I don't have A, so I'm going to copy it from my sheet. 3 0 0 negative 3 0 0 negative 3 3 0 0 3 negative 3, and then the rest one was just zeros. And then P, what was P? That was P, right? That's, yeah, okay. Yes, it's P here. So we have 1 0 0 1 0 1 0 1 0 negative 1 1 0 and 0 0 0 1. I hope I didn't copy wrong. Okay, so let's work it out. I'm working out these two first. There's no reason that I do this first, but I just do it. Okay, we go to this row and do the column, and etc. etc. Okay, so the first one is 3 plus all zeros. The next one is 0 0 0 0. The next one is 0 plus 0 plus 0 plus 0. Next one is minus 3 plus 0 plus 0 plus 0, so minus 3. Okay. Okay, second row. We take now this row and go to all the columns. 0 times, that's all zeros. That's all zeros. Then is a 0 times 0. Ah, wait, there is 1 times 3. Wait, let me do. Wait. So these two, and that's a 0, and that's a 3, and that's a 0. So a 3, and that's a 0. That's a 3 minus 3. So that whole thing is 0. And then okay. Now the next row, that's a 0, all zeros. Then it's all zeros. That's a 0 times a negative 3 plus a positive 3 times 0. So that is 0 again. And that is 0 plus 3 minus 3, again 0. And then the bottom thing is 0, 0, 0, 0. Quite a lot of zeros. Not surprising because our matrix itself had. Well, we need to get a diagonal form anyway. 1, 0, 0, 0, 1, 0, 1, 0, 1, 0, negative 1, 1, 0, 0, 0, 0, 1. That's the P that I'm copied. Okay, now we multiply again. This row, we work to this row. So that is a 3 plus 0, 0, 0. Then the next one is 0 times 0, 0, 0. So whole thing is 0. I get a 0, 0, 0, 0. I get a 3, 0, 0, negative 3. Ah, so this is also 0. Good, because otherwise I was wrong. Now the second row, take this row. 0, 0, 0, 0. 0, 0, minus 3. That doesn't sound right. Did I copy something wrong, guys? Okay, so, and of course now it's hard to see where I actually got my negative sign from. I wrote it down somewhere, but not the full thing. I have the feeling that I somehow copied something wrong. Let's see here. 1, 0, 0, 0, negative 1, 1, 0, 0, 1, 0, 1. Oh, I see. No, that's correct. That's correct. It's this one. Okay. Yeah. I'm sorry, guys. I don't know why it happened here. For some reason, this comes out a negative 3. Let's go on and see what else do we have. Yeah, you see the next one is also wrong because that's a 3 and it should not be 3. So there's clearly something, I somehow copied things wrong. But I don't see what it is anymore. Oh, I see. No. Ah, yeah. This column is 0, 1 here. I'm writing the wrong column here. This has to be a 1 and that's the 0. Okay. So let's do it over again. Sorry. Yeah, there's a bit of problem with this app. I like the app, but except for when you have to scroll back up. It's a bit of a pain. I can actually, no, let me not try to do this because, okay, so I copied this wrong. So it's 1, 0, 0, 0, 0, 1, negative 1, 0, 0, 1, 0, 0, 1, 1, 0, 0. Okay, let's work it out again. The first row, that is still a 3. Then I get that 0, 0, 0, so that's a 0. I get 3, 0, 0, 0. Oh, now I copied this one wrong. Jesus. Yes, now I'm correct. Okay, so that's also 0 still, and now I get 3 plus 0 plus 0 plus minus 3, that's a 0. Okay, this is still correct. Let's hope that the next one is correct. 0 times 0, I get still negative 3. What am I doing here? 0 times negative 3 times 0. So right, so that's not the only problem. Now this one is correct. 0 times 0 times 0 times 0. So 0, 0 plus 0 plus 0 plus 0. That's correct. Okay, I'm going to go on and then probably figure out. Well, now I'm multiplying with zeros rows, so this is always going to be zeros. So this is not the diagonal form I should have because I wrote down what the diagonal form was. So somehow I got a negative -1 slipped in somewhere. So exercise, find the mistake and then get a happy face. Okay, if you can find the exact time that I did it, it must have happened perhaps here with this switch. Perhaps, I don't know. It's somewhere with this something I switched around. Okay. But in any case, so this is the kind of question. But as I said, the 3 by 3, it's because it's so many numbers that it gets sometimes confusing. So I will ask you, a 4 by 4, I mean. I will ask you a 3 by 3 on the quiz, okay? All right.